5-minute reminder of our discussion from last time. Last time we were discussing spinors in Euclidean space. So we discussed spinors of SO2n and SO2n plus 1. We had this construction of gamma matrices, which you remember. So gamma 1 was equal to, what was it? Sigma 1 cross sigma 3. Gamma 3 was equal to identity cross sigma 1 times sigma 3, and so on. Gamma 2n, no, this was gamma 2, and this was gamma n. And then we had gamma n plus 1, which was sigma 2 cross sigma 3, and so on, up to gamma 2n, which was identity cross identity up to sigma 2. And this was up to n was equal to identity cross identity up to sigma 1. Okay, this obeyed did all the good things. We defined this charge conjugation matrix C, which was gamma 2n, n plus 1 up to gamma 2n. Oh, thank you. Yes. Right. We demonstrated that the charge conjugation matrix obeyed the following equation. So let's get the minus signs. Charge conjugation matrix obeyed the equation that C inverse gamma alpha C was equal to minus 1 to the power n times gamma alpha transpose. Okay. And then, using the fact that all the gamma matrices were Hermitian, we also basically it also followed that C inverse gamma star C was gamma C was equal to minus 1 to the power n gamma star. And in particular, it followed that gamma alpha beta C inverse gamma C was equal to well, let me get this right, star gamma alpha beta was equal to gamma alpha beta star. The point is that because there were two of them, this phase cancelled out, and anyway, we worked this out. Okay. Yeah. Okay. Then we also looked at what CC star was, and we found that this quantity was minus 1 to the power n into n plus 1 divided by 2. Okay. And we also explained that SO2n had chiral spinors. Okay. We also defined gamma 2n plus 1, which was I to the power n gamma 1 up to gamma n. This
gamma alpha beta star,
yes,
is also gamma alpha beta transpose, right?
With the minus sign. Because you see, gammas are Hermitian, but gamma alpha beta is anti-Hermitian because of the extra commutator. Okay? And right. So
why you are writing it differently for different, like for one index gamma you are writing transpose?
the reason I wrote this, I could write anything I wanted, but the reason I wrote this was we were interested in seeing how things transformed under SON. And gamma alpha beta were the generators of SON. So we wanted to see how if psi transformed in some representation of SON, we wanted to see how how psi star transformed under SON. So that is the question of how gamma alpha beta stars. That's why I wrote that specially. Okay, you can work it out for anything you want. But this was specially important because it was the SON transformation matrix. Okay, great. Okay, we had this. we also had this definition, and then we argued that if psi was chiral. So you remember that we argued that this gamma 2n plus 1 in a suitable basis took the form 1 minus 1 0 0. Thank you. Yes, up to gamma 2n, yes. We argued that this gamma 2n plus 1 in a suitable basis took the form 1 minus 1 0 0. It had as many plus 1 eigenvalues as minus 1 eigenvalues, 2 to the power n minus 1, plus 1 eigenvalues, 2 to the power n minus 1, minus 1 eigenvalues. The projectors p plus minus equals 1 plus gamma 2n plus 1 by 2 projected spinors, okay. So gamma 2n plus 1, remember, played a different role in SO2n and SO2n plus 1. In SO2n plus 1, it's just another gamma matrix. It obeyed all the properties of the gamma matrices, including that complex conjugation properties. Okay, so it was just another gamma matrix. In SO2n, it was not one of the gamma matrices, but an object that we could use to produce projectors. We argued that since gamma 2n plus 1 commuted with all the generators of SO2D, this projector was one of these matrices that by the Schur lemma tell us we have two different representations. Okay, and using these projectors, we projected onto the two different representations of chiral spinor and antichiral spinor. We argued that the chiral spinor under complex conjugation went back to itself if n was even, but went to the antichiral spinor if n was odd, and vice versa. Okay, and then we ended the last lecture with this table, which said that if we were looking at Euclidean space, so SO2n or SO2n plus 1. So let's first do SO2n plus 1. We found if n is equal to okay, they've written a 0, 3 mod 4. We get real spinors. And if n is equal to 1, 2 mod 4, we get pseudo-real spinors. Where remember what real and pseudo-real meant? Remember, real spinor was a spinor that obeyed the equation psi is equal to C psi star. We argued that, if you remember, we argued that C psi star and psi star and psi behave the same way under SOD transformations, SO2D transformation, SO2n transformation, sorry, 2n plus 1 transformations. Okay, so this was an equation we might want to try to impose. It was representation theoretically a sensible equation. Okay, but it was an equation that either had solutions or didn't, depending on details. When this equation had solutions, we called the spinors real. When the equation had no solutions, we called the solution the spinors pseudo-real. And you remember that in the case where it's pseudo-real, we instead commented that we could impose the following condition: C gamma ij psi star, where gamma ij equals the symplectic matrix. Something that is of the form 0, 1, minus 1, 0, 0, 1, minus 1, 0. The properties of gamma ij that we will use is that it's antisymmetric and that it squares to minus 1. Okay, and from the fact that it's squared to minus 1, the integrability condition, the obstruction to imposing this equation, went away if you in pseudo-real dimensions, went away if you added this gamma ij, omega ij. Okay, so that was what we found for SO2n plus 1, and for SO2n, the reality or pseudo-reality was the same. Same condition on n. Okay, the new element was that spinors, chiral spinors were either real or complex. Okay, so here in 0 dimensions or 0 mod 4, chiral spinors were real. So 0 mod 4, we had real spinors. Real chiral, where I always mean real chiral spinors. Okay, now in 3 mod 4, n is odd. So chiral spinors, the complex conjugate of chiral spinors and anti-chiral spinor. So that's the situation which we just call complex. 3 mod 4 or 1 mod 4. Right? You try to complex conjugate a chiral spinor, you get an anti-chiral spinor, there's nothing more to say about it. Okay? And in n is equal to 2 mod 4, we had pseudo-real spinors. Okay, this is so this table we worked out, but let me just give you 1 or 2 quick examples. The nicest dimensions, the dimensions where you can consistently impose the most conditions, are dimensions where SON, where we are doing SO2n. So you can impose a chirality condition and a reality condition. Okay, that is the even guy with real spinors. Well, what was that? That only happened in 0 mod 4. Okay, so in some sense this was the nicest dimension for spinor, the dimension in which you could impose a maximum number of conditions. Okay, 0 mod 4 means SO8, SO16, SO whatever, 24, SO32. Okay, SO8 from, since all of you guys know group theory really well, SO8 is a beautiful group, right? It has this fantastic triality property. The 3 8-dimensional representations of SO8, namely the fundamental representation, the spinor, the chiral spinor and the anti-chiral spinor, actually are all on the same footing. There's this triality that allows you to convert fundamental to chiral spinor to anti-chiral spinor, and anti-chiral spinor to fundamental, and to keep going. You know, it's a really beautiful group. One part of that beauty is that you know that the fundamental representation of SO8 is a real representation. One part of that is that the chiral spinor is also real. Right? Okay, so this is a very nice dimension. Another dimension we might be interested in is another dimension that's of particular interest to us sometimes is n is equal to 4. Sorry, n is equal to 2, so SO4. Euclidean 4-dimensional space. In that dimension, we have spinors are sort of real. Spinors are not complex. This you're very familiar with, right? That we have these two spinors of SO4, and these are the fundamental or anti-fundamental of SU2 times SU2. Right, so fundamental of one SU2 is fundamental of the other SU2. Sorry, I shouldn't have said fundamental times. Fundamental of the first SU2 and the fundamental of the second SU2. These are the two spinors. They're completely different. Clearly, if you do some complex conjugation on the first SU2, it doesn't relate to the second SU2. So it's not a complex representation. That you know. Okay? But what we discover from this is that it's pseudo-real representation. That is, you can't consistently put to the condition that the spinor is its own star on one spinor. You need at least two of them with this omega ij map.
In SO4 under complex conjugation, the first goes to second, right?
There are two kinds of complex conjugation. There's the complex conjugation that comes from analytically continuing complex conjugation in Lorentzian space. That does first goes to second. And that is often what is relevant for physics. But there is a second kind of complex conjugation if you're just thinking of SO4 as a group. You're not thinking of it as looking at the hermiticity conditions from SO3, 1 and then analytically continuing that. Okay? There, suppose you gave it to a mathematician, the mathematician would tell you SO4 is SU2 times SU2. You must be crazy if you think complex conjugation switches the two SU2s. You can do that. You can define a new complex conjugation operation. But it's not the normal natural one you would do if you were just looking at it.
Because in SO3, 1 the boosts are anti-emission. So
Exactly. So this is what we always do in physics. Our reality conditions in physics are always in real time. Always in physics, I mean, when I say in physics, when the physics is that of a real time situation. Always, Euclidean space is a calculational tool. And the reality conditions in Euclidean space are not those that may seem natural to you in Euclidean space. They're the ones that you get from Lorentzian space after analytically continuing. Okay? So this interplay we will see many times in our course. It's going to be especially important when we look at superconformal algebras. Okay? But great. So that's another dimension that's sort of interesting. And the other things to keep in mind are the following. If we were in, when do we have real odd dimensional spinors? Well, SO6 has real spinors. There's no question, sorry, SO7 has real spinors, right? Because 3 plus 1, 2 into 3 plus 1. SO7 has real spinors, and SO1 or SO9 has real spinors. No question of chirality because it's odd. On the other hand, SO3 and SO5 have pseudo-real spinors. SO3 having pseudo-real spinors is the same thing as SO4 having pseudo-real spinors. Because you saw SO3 was SU2. And the fact that you could not consistently impose a reality condition on spinors of SU2 is the same thing as not being able to consistently impose a reality condition on spinors of SU2 times SU2. Okay, so all this is we've derived it and it's sort of familiar, and of course you won't remember all of it, but it's worth knowing where you can quickly go to a table that looks up these properties. It's a useful thing, yes? Can't hear you. Yeah, there's no complex spinor in SO2n plus 1. There isn't because, as we argued last time, in SO2n plus 1, the representation, the Clifford algebra, the space on which the Clifford algebra acts, is an irreducible representation. Okay? Complex means you take the complex conjugate of that representation, you go to another representation. Because this was irreducible, you came back to the same representation. Okay? So there's no complex representations. They're either real or pseudo-real. Okay? What complex was for SO2n was when you took a chiral spinor and became an anti-chiral spinor. But there's only one representation of SO2n plus 1, so the question doesn't arise. Okay? Yes?
For SO3, the C will be just identity, right?
What?
For SO3, C will be identity. So it is like psi equals to psi star.
SO3, why would C be identity? Let's try. C was a matrix that transposed everything. Okay? So C would be basically sigma 2. Right? So the three sigma matrices are sigma 1, sigma 2, and sigma 3. Okay? Now if we take C is equal to sigma 2, for instance, okay, then we will have sigma 2, sigma 2 is its own inverse, sigma mu, sigma 2. If we take it through sigma 2, we just get back sigma 2, but that had opposite transpose. So this would be minus sigma mu transpose. Okay? And the fact that sigma 2 times sigma 2 star, which is minus sigma 2 times sigma 2 dagger, which is minus sigma 2 square, is minus 1, is the statement that SU2 has only pseudo-real rather than real representations. Recall? The condition for reality or pseudo-reality was whether CC star was plus 1 or minus 1. All good? Okay, so this is something famous. Somewhere in your education you've seen this. That you cannot put. You cannot make SU2 spinors real or SO3 spinors real. Okay, good. It's sort of equivalent to the following question. It's sort of equivalent to the question, can you choose your sigma matrices? You know, in dimensions where the spinors can be made real, one can prove that one can always find a representation of the gamma matrices which are either all completely real or completely imaginary. Okay, so that the sigma mu nu's are completely real. Sigma, gamma alpha betas are completely real. Then it's obvious you can put a real representation. Okay, and the fact that when you look at the Pauli matrices, at least one of them had to be imaginary was basically the fact that it was a pseudo-real representation. Good. Other questions or comments? Okay, excellent. Now we want to upgrade our understanding of spinors to Lorentzian space, since that's where we really do physics. Okay, so we want to now try to understand. What happens to spinors of SO2n, comma 1, that would be the analog of the odd guy, or SO2n minus 1, comma 1, this would be the analog of the even guy. Okay, so what do we want to do? We want to just play the same game. Our gamma matrices have to obey the algebra gamma alpha, gamma beta, and the commutator is equal to 2 eta alpha beta. We will always use the mostly positive convention through this course. Okay, so we'll have some minus 1 and then 1, 1, 1, 1, 1, 1. Okay, and as we discussed in answer to Kanu's question at the end of at some time in the last class, there's a very easy way for getting the representations of the Clifford algebra which obey these commutation relations, starting from the Clifford algebra that obey those commutation relations. All you have to do is take one of the gamma matrices and multiply it by I. Okay, so we have to choose one of the matrices. Let's make a choice. What we will say is gamma 0 is equal to I times gamma 2n. Gamma 2n. Let me check. I'm following his convention. Yes. Right. So we have gamma 0 is equal to I times gamma 2n. Okay. Once we make this choice, it's clear that we obey the Clifford algebra for Lorentzian space. Okay. Now we want to see how much of what we've done changes because we put this additional factor of I. Okay. First, what about the definition of gamma 2n plus 1? Well, remember gamma 2n plus 1, we want to define it so that it squares to 1. We chose our I factor precisely to achieve that. That we're not going to change. Okay. So gamma 2n plus 1 does not change. Okay. So gamma 2n plus 1 remains gamma 1 to gamma 2n into I to the power n. And if we want to write this in terms of gamma 0, we'll write this as not minus I to the power n. And I to the power n times minus I times gamma 1 to gamma 2n plus minus 1 gamma 0. Right? Because minus I times gamma 0 is gamma 2n. If we want to write in terms of new gamma 0s, this is what it is, which is the same thing as minus I to the power, let's say, n plus 1. Or perhaps even better to say I to the power n minus 1 times gamma 1 to gamma 2n minus 1 gamma 0. Okay. What? I'm doing this either for SO2n minus 1 comma 1 or for SO2n comma 1. Right? For both of them, this construction will work. Because all we wanted for the
Any gamma,
you can change any gamma you want.
It
Yeah. Yeah, it didn't need to be the last.
Yeah, yeah.
Right. So I will always change the gamma to n. Okay? Great. Next question we have was, let's go down this list. Okay. So we have our construction, right? We just have to put an extra factor of I in gamma to n. So that hasn't changed. We have what about C? Let's just use, we can either use the same C or put an I. It makes no difference. Sorry, there was an I in? N minus 1 does it, right? There was minus times gamma I times to the power n plus 1, but I squared is minus 1. So, is this correct? Okay. Okay. So, we could either change our definition of C or not by an extra factor of I. It will make very little difference. You remember that every good property of C had to do with either C inverse, one factor of C and one factor of C inverse, or C star. In either of them, multiplying C by I doesn't change either C times C inverse or C star. Is this clear? Okay, I think just to follow this guy's convention, I'm going to change the definition of C. So C is now going to be defined as gamma n plus 1 up to gamma 2n minus 1 and gamma 0, which therefore is equal to I times C old. Okay, just for fun, just because somebody else has done it, we're doing it. It would make no difference. Hello? No, will not change. Will it change? Let's see. So I inverse is equal to minus I. So I times minus I is equal to 1. Okay. Excellent. So nothing changes, but it's a matter of convention. We choose some convention. Fine. Then let's go down this list. Let's keep going down this list. What about these properties?
You have not changed. You have done an active change in the representation, or like I'm asking that I'm saying in gamma 2n plus 1 instead of gamma 2n you should have written gamma naught without the I, or
In gamma,
the definition is same.
if I had written gamma naught without the I, my gamma 2n plus 1 would no longer have squared to 1, because it was squared to minus 1, because there would be an extra I square. The way we chose the factor of I,
Renaming of gamma 2n as minus I gamma naught, that's all. And then you are calculating the gamma naught and then you are putting it everywhere in this list.
wait, but you see gamma 2n plus 1 had to be product of all the gammas, and then the factors to be chosen so that it squares to 1. Okay? That if you could if you wanted to say it's product of gamma 1 up to gamma 2n, times some factor and choose that factor so that it squares to 1. And that factor then would get an extra factor of I compared to what we had earlier, because gamma naught has an extra factor of I compared to gamma 2n. Okay? So this was not a matter of convention. This was forced on us. Because it's a physical question. Does gamma 2n plus 1 square to 1 or not? Is this clear?
So then gamma naught square should go to minus 1. That's why
It is minus 1. Right? Because gamma 2n squared was 1 and gamma naught is I times gamma. Okay? It's also minus 1 because we wanted it to be minus 1 from the Clifford algebra. Okay? All clear? Excellent. Now let's look at this part. We wanted to know what happened there, right? What's the analog of this? C inverse gamma alpha C is equal to minus 1 to the power n gamma alpha transpose. this does not change at all. You see, because all we have done is to change one of the gammas by multiplying by I. Multiplying by I doesn't change how it changes under transpose. I just cancels on both sides of the equation. And as Kanu helped us understand, the extra factor of I in C doesn't matter in C inverse times C. So this equation continues unchanged. Okay? So this equation, all good. Right? Now what about this equation? Here there is a change. Because star changes if you multiply something by I. Okay? Star changes if you multiply something by I. So this equation is going to change. And I'm going to help us let us try to understand. Let us try to understand how what we should do to get a good equation. Okay? So let's try to recall that gamma alpha dagger. Okay? Now this is equal to gamma 0, gamma alpha, gamma 0. Let's check this. If maybe it's up wrong by minus sign, we'll check it. Okay? Let's choose one of the gammas that was not gamma 0. Let's choose alpha to be not gamma 0. Then taking gamma 0 through gamma alpha, taking gamma 0 through gamma alpha gives you a factor of minus 1. But gamma 0 squared also gives you a factor of minus 1. So the equation works. Okay? On the other hand, if you choose this to be gamma 0, then taking gamma 0 through doesn't give you any factor. Gamma 0 squared is minus 1. But gamma 0 dagger is minus gamma 0. Because we now multiply by an extra I compared to gamma to n. So this also works. So this is a true equation. Okay? So now we can use this equation to understand what we get with stars. Okay? So gamma alpha dagger is equal to gamma star transpose, or gamma transpose star. Okay? So we have gamma alpha transpose and then star is equal to gamma 0, gamma alpha, gamma 0. Right? But gamma transpose, okay, gamma transpose was equal to C inverse gamma alpha C times minus 1 to the power n times star, the whole thing star. Right? That has not changed. That's this equation up here. Okay. So this is equal to gamma 0, gamma alpha, gamma 0. Okay. And now we write this as minus 1 to the power n C inverse star gamma alpha star C star. Okay. And we want an equation like this. So we multiply out by let's say minus 1 to the power n gamma alpha star is equal to, or let's put the minus 1 to the power n on this side, is equal to C star gamma alpha C. Okay? All good? Now we have to work out what it is. C star gamma C star inverse. Okay. Sorry. Sorry. C star, gamma 0, gamma alpha, gamma 0, C star inverse. Okay. Now let us also work out what the relationship between C and C star is.
Either -1 or 1, right?
Or some I, let's see. Yeah, minus 1 or 1. Yeah, minus 1 or 1. Right, so we have to work it out. So what was C? C was, well, actually we worked it out last time. Can somebody remember what was C times C star? C star was just minus 1 to the power n times C, because it was just a product of n different imaginary matrices. So now it's just minus 1 to the power n minus 1 times C. Because now gamma 0 is no longer an imaginary matrix. Okay, so C star is just minus 1 to the power n minus 1 times C. Right? So we just plug this in. This factor times the same factor in C star inverse goes away. Right? Because minus 1 inverse is minus 1, or plus 1 inverse is plus 1. Okay, and so we have gamma alpha star is equal to minus 1 to the power n C gamma 0 gamma alpha gamma 0 C star. C inverse. Thank you. Okay, and therefore we get that gamma alpha beta, which was just a product of gammas. If we take that star, we use this relationship for each gamma, so let's work that out. So gamma alpha is alpha beta is gamma beta minus something else. Okay, now if I star this gamma alpha beta star, that's just this star times this star. Right? So you get minus 1 to the power n plus 1, but so that cancels because it comes twice. Then you get C gamma 0 gamma alpha gamma 0 C inverse C gamma 0 gamma beta gamma beta, then gamma 0 C inverse. All good? Minus the other. I'm just working on one term. They'll all work the same way. Okay? Now we have to, C inverse times C is 1. Gamma 0 times gamma 0 is minus 1. Okay? And so we get is equal to C gamma 0, gamma alpha, gamma beta, gamma 0 C inverse. Minus 5. The other term clearly will work the same way. Algebra doesn't care about alpha, beta, beta, gamma. And so we have gamma alpha beta star is equal to minus C gamma 0, gamma alpha beta, gamma 0 C inverse. Okay, and if you want, you can write this as without the minus sign and putting an inverse here, right? Because gamma 0 inverse is minus itself. To make it clear, it's a similarity transform. Okay, what is the point of this? What is the point of this equation? The point of this equation is that we can now try to impose a new reality condition on spinors. Okay? The point of this equation is we can now try to impose a new reality condition, and the reality condition we will try to impose is psi star, is to consider the quantity C gamma 0 psi star. A bit louder, Kanu. We will eventually consider that. I just want to look at this quantity and see how it transforms. And then we will see that it transforms the same way as psi. Okay? So let's look at this quantity. How does it transform? So remember that delta of psi was equal to gamma alpha beta psi. That's how psi transforms under an SOD transformation. So we want to know what is delta of C gamma 0 psi star. So that is the same thing as C gamma 0 by definition. Gamma alpha beta star psi star. Clear? Okay. Which is equal to C times gamma 0, and now we add this thing here, times, did I want to put, C inverse? Wait, it's a bit odd. What?
C gamma 0 on the right.
Say again, sorry?
Can we put C gamma 0 on the right side of psi star?
We can, but what did we do last time? Sorry.
C psi star. Yeah.
We did C psi star, right? How did it work last time? What's just as a reminder, sorry. The thing without the there we had, I hope we've not got the C inverses.
So delta psi star was,
Last time it was C inverse gamma C.
Sorry?
C inverse gamma alpha beta star.
Gamma.
Yeah, that was C inverse gamma alpha beta C in the left.
Yes. C inverse. Sorry. Yeah. But let's just do what we did last time. Sorry. So, what did we do wrong here? Just a minute. So I should have put a C inverse C. Thank you. Nothing is going to change. The C inverse and C, nothing is going to change. Sorry. So everywhere we will have just the C inverse and C replaced. What? C is C inverse. It's a good point. Is C inverse? Is C inverse?
you were asking why we ended up.
No, sorry. What? Not quite, because C square is not always 1. Why? Let's just go through this algebra again. Yeah. Sorry.
Up to that minus sign, this is true, right?
It's nothing matters, because if you put a minus sign here and a minus sign here, it cancels.
Yeah.
So nothing matters. We could have put C inverse and C.
You just put minus 1 to the power n minus 1 in both terms.
Yeah.
And then you can change it to C or C.
It doesn't matter at all.
Yeah.
Right? But just if we were to do the algebra correctly from the beginning, we would already have got C inverse. Okay? But so just so that you don't go home feeling unsatisfied, let's look at that. Okay? So this equation here, where did we start? We started with this equation. That was okay. This equation was okay. Therefore, this equation was okay. Therefore, now here we put transpose is equal to C inverse gamma C. That was okay.
I think you have to use, yes, in the set, this is correct because you have to multiply by C in the left to get rid of the C inverse. And in the right it have to be C inverse. So you eventually have to use that relation C inverse is C times some.
Yeah, just for my satisfaction, last time what did we do? Last time we had this relation or the other one? For
Last time gamma was C inverse gamma.
Gamma transpose was directly gamma star.
yeah. No, but the inverses, how did they work out? Gamma star was was C inverse gamma C. Gamma star alpha beta was C inverse gamma C.
Yes.
Okay, good.
All I was trying to say ki
Ah,
gamma alpha beta star
ah.
is C gamma alpha beta C inverse.
Okay, fine. I agree. So Schumann's point is that we can just change C and C inverse differ by either 1 or minus 1.
And that will cancel.
And if it's 1, it's the same as C inverse. If it's minus 1, it's also the same. So we're just going to make it C inverse. Okay. Okay. I'm going to write it this way, just so that I don't have to write C inverse in the reality condition. None of it matters because they all are proportional to each other up to a minus sign. But just to stick to everyone's conventions. Okay, sorry about that. So, yeah, so let's go on. Right. So now we don't need a reminder. Okay. So now we'll be good. So this gamma alpha star. Sorry. We had a C inverse here, right? So I'll make this also gamma inverse. Right? Because we actually had a minus sign. We took one of the gamma zeros to gamma 0 inverse. Which one doesn't matter. Okay? So this is the final relationship we'll use. Okay, and now we're good. Now we're good because we get, oh my God, I wanted the opposite orders. Okay, I'm so sorry, but you know, gamma 0 either goes through C with a minus sign or with a plus sign. If it goes through C with a plus sign, it's the same on both sides. If it goes through C with a minus sign, I'm so sorry. We want to write this as C gamma 0. And gamma 0 inverse zeros. They're all equivalent. I'm so sorry. Okay. And now are we really good? Are we really good? Yeah. Okay, great. So now we write this as gamma 0 inverse C inverse gamma alpha beta C gamma 0 psi star. Okay, and these two cancel now. So this is equal to gamma alpha beta on C gamma 0 psi star. Okay, sorry for that mess up. Okay, sorry for that mess up. So we've so what is the conclusion? The conclusion is that C gamma 0 psi star transforms under SO D or whatever SO group in exactly the same way. As psi itself transformed. Because delta of C gamma 0 psi star is the same formula in terms of C gamma 0 psi star as delta of psi was in terms of psi.
In the above formula, gamma alpha beta star.
Yes.
So this was C inverse, sorry, gamma 0, if you do it correctly, then the line was gamma 0 inverse C inverse, and then C gamma 0.
Have we got a minus sign off, you're saying?
Yeah, I am getting plus sign. If you write that line, I think from where you are saying that you are getting the gamma 0.
This line you agree with?
Yes.
Okay. So if you agree with this line, let's go on. C inverse C cancels. Gamma 0 cancels. Gives you a minus 1.
I am saying
No, at the moment there are no inverses. Right? I just put in that.
Okay. Oh, you use the minus sign to make it inverse.
Yes. Yes. Okay. Please check the algebra. I think it's correct. Okay, all good. So now, as Kanu suggested, we now are sort of ready to go. So what we want to do is now to try to impose the condition psi is equal to C gamma 0 psi star. Of course, we should actually impose it with an arbitrary phase. But we use foreknowledge that the phase is the right one, meaning that it's the right modulus, and phase doesn't change whether we can do it or not, like we saw last time. We'll see the same thing here. Okay? We should really say psi is equal to alpha C gamma 0 psi star, and then try to find an alpha for which this is true. Turn out that mod alpha will be equal to 1, and the integrability condition for this equation will only depend on mod alpha, so I'm not cluttering up the notation by doing that. Right? Okay. So now we just proceed as we did before. Okay? If we can impose this equation, then we can use it twice. Okay? So if we can impose this equation, we can use it twice. So we can write is equal to C gamma 0, and then psi, the whole thing star, but psi was from here, C gamma 0 psi star. Star. Right? Or you could equivalently say star this equation. I don't know, there are many ways of doing it. We could have started this equation and then used it. But okay, fine, I'm just doing it this way. Okay, so this is equal to C gamma 0 times C star gamma 0 star times psi. So for this equation to be imposable, we need that the matrix C gamma 0, C star gamma 0 star have eigenvalue 1. As we will soon see, this equation, this matrix will be either plus 1 or minus 1. It's plus identity or minus identity. So this equation can be imposed if that matrix C gamma 0, C star gamma 0 star is plus identity, and cannot be imposed if it's minus identity. Cannot be imposed in a real rather than pseudo-real way if it's minus identity. Okay? So we just have to figure out what the mechanics of this, we have to figure out how this matrix goes. Okay, so first thing, let's do the following. First, let's take gamma 0 through C star. Okay? What? We already know C star. C star is basically a product of n gamma matrices, one of which is gamma 0. So taking it through C star gives a factor of minus 1 to the power n minus 1. Okay, so we get is equal to C star times gamma 0 star, okay, times minus 1 to the power n minus 1. Right? Which, now, what is gamma 0 times gamma 0 star? Remember, gamma 0 was real, because it was gamma 2n, which was imaginary, and then we multiplied by a factor of I. So gamma 0 star is same as gamma 0. So gamma 0 times gamma 0 star is minus 1. So this is equal to C star into minus 1 to the power n. But C star is the same as what we had before, because C only changed by a phase, but that phase cancelled out in C star. Okay, so we can read off what C star was from here, and so that is equal to was it n plus 1, n minus 1, just to make sure. Not that it makes much of a difference, but yeah, n minus 1. And yeah, it makes a difference. Sorry, this one was n minus 1. So we add a factor of n. So this is minus 1 to the power n into n plus 1 by 2. Was it n to n plus 1? I'll check, sorry. N into n plus 1, then this becomes n to n minus 1. Thank you. Right? Because 2n. So, yeah?
Gamma 0 square is minus 1, right?
Yes.
So gamma 0
Stop. No, because gamma 0 is now real. Because gamma 0 was gamma 2n, and then we multiplied by I.
Yes, and gamma 0 square will be minus I, so I minus I.
No, but remember, gamma 2n was itself imaginary. Right? The n gammas, gamma n plus 1 up to gamma 2n were imaginary.
So you are saying gamma 2n star is minus gamma 2.
Yes. Right? Remember our construction. The first n gammas were real and symmetrical. The next n gammas were imaginary and antisymmetrical. Okay? So we took gamma 2n, which was an imaginary matrix, multiplied by I, we got a real matrix. So gamma 0 star is equal to gamma 0. Clear? Okay, yeah. Okay, excellent. So we get minus 1 into n minus 1 by 2. I'll just check that this is what they get as well. Yeah, great. They get the same answer. Minus 1 into n minus 1 by 2. Okay, and now you see reality can be imposed if minus 1 into n minus 1 by 2 is plus 1 and cannot be imposed, pseudo-reality, in the other cases. Okay? You can go ahead and check that the business with the gamma to n plus 1 does not change. That is, nothing we've done here changes the fact that if you take psi, which is a positive chirality matrix, and look at C gamma 0 psi star, then that matrix will become a negative chirality matrix if n is odd, and positive chirality matrix when n is even. Why did we know it cannot change? Because you see, this is a fact of representation theory. It's a fact of complex representation theory. As a complex Lie algebra, chiral and anti-chiral spinors, okay, map to each other under shifting all weights from pluses to minuses. Okay? So that could not change by some choice of reality conditions. Right? It's just in the representation theory of the Lie algebra, when you switch weights to minus weights, this happens. But it's a 5-minute exercise or 3-minute exercise to go ahead and check it anyway. Okay, I'll leave that for you to do. Just along the lines of what we've been doing. Okay, great. So now we are ready to build our table for Lorentzian spinors. Nothing, okay. Okay, so let's once again start with the SO odds. So let's start with SO to n plus 1. Okay, when? Can't hear you. 2n comma 1, thank you. Okay, let's start with that guy. Okay, now let's look at n is equal to 0. Okay, that remains good. So n equals 0 mod 4 is real. What about n equals 1 mod 4? 1 mod 4 also is now good. So 0 comma 1 mod 4 is real. What about n equals 2 mod 4? That's pseudo-real, right? Because 1 into 1 What about n equals 3 mod 4? That's also pseudo-real because 3 into 3. Okay? So n is equal to 2 comma 3 mod 4 pseudo-real. Okay? And of course, there's no question of SO2n plus odd things being complex or real. I mean, being complex, that doesn't make any sense. Okay, so that ends our table for SO2n comma 1. What about for SO2n minus 1 comma 1? Okay? Well, same reality or pseudo-reality properties, except, of course, as always, if n is equal to 1 or 3, we have complex. This has not changed. Always mod 4. I'm not writing the mod 4. Okay? What about n is equal to 0 mod 4? We have real. And n is equal to 2 mod 4. We have pseudo-real. Okay? So, let's see. N is equal to 0. So, when do we have complex spinors? Okay? So, we have complex spinors in, what am I saying? Something's wrong. Something's wrong. Just a minute. No. Yeah. So I said something wrong. My argument about the. Okay. I gave you a convincing argument about complex and real, and it's wrong. So let's just work it out. Why is it wrong? Just a minute. Anyway, so I got the complex real wrong, apparently. Let me work that out. Sorry. This makes no sense because we know that in two dimensions, spinors are real, a chiral real. We use that all the time. Right? It makes no sense. Sorry, I said something wrong. Let me back up and work out what I said was. You could check. I'm just going to back up and work that out. Okay, this is wrong and has to be corrected below. This part is okay. Okay, the chirality part I got wrong. Let me work that out properly. What? Well, I told you that the complex, real and complex, whether it's real and complex, does not change from SO. It does not change when we change the signature. And I thought I had an argument for it, but apparently it's wrong.
In SO3, 1, we can impose this condition for pseudo-reality, right?
For SO3, but it doesn't work for SO1, 1. For SO1, 1, sorry, just a minute. Let me make sure. Let me make sure the labeling for n equals 1 here is SO1, 1, right? And that would tell us it's complex, which is nonsense. It's SO1, 1, two-dimensional world sheet of the string. We have chiral real spinors, definitely. Okay, another way of saying it. What? For SO2 we had complex, that's correct. But for SO1, 1 we don't. Why? Because we have to change one of the Pauli matrices. Change sigma 2. All Pauli matrices are real. So it's definitely wrong. Let me first work it out with algebra and then I'll try to understand why my slick argument was wrong. Okay. Let me just work it out with algebra. Okay. Remember that our condition was psi star. Psi was equal to, what was it? C gamma 0 psi star. Okay. So the question that we are asking is the following. If I start with psi being a chiral spinor, okay? If I start with psi being a chiral spinor, what is C gamma 0 psi star? Okay. So we know that psi, because it's chiral, is equal to 1 plus gamma 2n plus 1 divided by 2 on psi. We know this. So we will put this in. Okay. So we will say C gamma 0 times 1 plus gamma 2n plus.
Gamma 2n plus 1 is there for SO 2n minus 1.
Why not?
That's where in even dimension there.
In even dimensions, it's always there.
Understood it.
Yeah. Right? So, this quantity, if I do this quantity on a chiral spinor, that's the same as this. Okay. Now, what do I know about starring? So the half, of course, this just goes through. I want to know how this goes through gamma 2n plus 1. So I want to know C gamma 0, gamma 2n plus 1 star. I want to write this as something times gamma 2n plus times C times. I want to write this as plus minus gamma 2n plus 1 star times C gamma 0. Okay. So now let's go up and look at some relations we had. There, that's the relation I wanted. That's probably the, let's check. So we have gamma alpha star is equal to, I'll write it down. Gamma alpha star is equal to C gamma 0, gamma alpha, gamma 0 C inverse. Hang on for 1 minute, let me just write this down. So we had gamma alpha star was equal to, can somebody remember, minus 1 to the power n? C gamma 0, gamma alpha, gamma 0 C inverse. Okay, great. So now, let me, first I can switch order and switch C inverses as we did last time. Cost of no sign and no anything. So I can write this as equal to, no, right. Oh, maybe first multiply here. I want C gamma 0 on that. Fine. So let me make this gamma, I'm going to make this, please check if you agree. This I'm going to make C inverse, first step I'll make C inverse and gamma 0 inverse.
Then 1 minus.
Hang on, gamma alpha, right, first I'll just do this. Gamma 0 C, this is okay without any sign. Then I want this to be, I want to first take this through here, which is equal to minus 1 to the power n times gamma 0 C inverse, gamma alpha C gamma 0. That's again no sign, no cost, same phase on both. Okay. And now I'll write this as a gamma 0 inverse. So gamma 0 inverse is minus of gamma 0. So this is equal to minus gamma. Okay. So this is the formula I'm going to use. Okay. So now when we want to get it through, so that tells us that C gamma 0, gamma alpha star, gamma 0 inverse C inverse, or maybe even better, gamma 0 star is equal to gamma alpha C gamma 0 with a minus 1 to the power n minus 1. Right. So it tells us that we can take C gamma 0 through gamma alpha star. It becomes gamma alpha and gives us this additional phase. Okay. So now we just take it through everything that appeared here. Okay. We take it through everything that appeared there. It just seems to give us no phase, right? What have I done wrong? Sorry. Give me 1 minute. C gamma 0, gamma alpha star. How did it work last time? I'm so sorry. How did it work last time? What? What? What's the problem? When I work it, take it through, I'm getting no phase. What? But it will appear, this phase will appear 2n times. We go all the way through, right? Right, we keep going. Each of the gamma alpha stars has become gamma alpha. So since it's an even number of times, I just get no phase. I'm sorry. But this problem should have occurred also with SO2n. But we got a sign. How did that work? There was no gamma 0, but that doesn't seem relevant here. We took C through, taking C through produced I'm doing something. Give me 1 minute more. So what am I doing wrong? Ah. Yeah.
Use that gamma alpha star formula directly in the gamma 2n plus 1 star. What he's trying to do. It works with 2n.
Yeah.
Then lot of gamma 0 C inverses would cancel out and
That's what I was trying. What I was trying was to use that C gamma 0 times gamma 1 up to gamma 0 to n minus 1 gamma 0 star. Right, this is what I wanted. Then I took this guy through here, I got a sign. I unstarred it and got a sign according to this formula. Then I took it through again. Again, I unstarred it and got a sign. And I kept going. But I got the sign to the power 2n. So that's nothing. Right? What am I doing wrong? So sorry. So sorry. Give me one minute.
there is a I to the power n, right? That will give a minus 1 to the power n.
Yeah.
Good point. Thank you. Thank you, Kan. Okay, very good. So, thank you. Okay, good. Excellent. Thank you. That was the key point. Yeah. So as Kanu pointed out, everything we said here was correct, but now it's important that we write gamma 2n plus 1 as equal to I to the power n minus 1 times gamma n plus 1 up to gamma 0. For using this formula, it was important that we wrote it in terms of gamma 0. Right? Thank you, Kanu. That's it. Okay? So that's the difference between the previous case. Yesterday, we went through the same algebra, and yesterday also we got the same formula, minus 1 to the power n from the I to the power n. But this time there's an I to the power n minus 1. Okay? So because we've got this I to the power n minus 1, now we find that we get that, so what have we found? We found that from here, that this is 1 plus minus 1 to the power n minus 1 gamma 2n plus 1 over 2 times C gamma 0 psi star. Right. So now what we see is that we take a chiral spinor, we take its complex, we take C times gamma 0 times psi star of it, and that spinor has become antichiral. Okay? That spinor has become antichiral if n is even, opposite to what we had before. It's become antichiral if n is even and chiral if n is odd. Okay? So this extra -1 was sort of very crucial. Thank you, sorry for the mess up. Thank you. Okay, I will try to fix my abstract argument last time, it was wrong. I will try to fix it. It's probably because complex conjugation has an extra I. So I will try to fix that abstract argument. It was a bullshit argument, didn't work. This is correct algebra, it works and gives you the right answer. Thank you, Kanu. Okay, so now let's go and recover our incorrect formula. So we get 0 and 2 as complex. Okay, now when was it real? Real was n is equal to 1 mod 4. And when was it pseudo-real? Pseudo-real was n is equal to 3 mod 4. Yes, this is correct. Okay, excellent, 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 excellent. And so now what's to remember here? What's to remember here is that S, 2 Lorentz dimensions has real Majorana spinors. 10 Lorentz dimensions also has real Majorana spinors. Okay, because 1 mod 4. So 1 was SO 1 comma 1, which was 2 dimensions. And 10 was SO 9 comma 1, which was also 1 mod 4. Okay, so interestingly enough, the 2 dimensions that are especially important to string theory, 2 dimensions because that's where we formulate the theory on the world sheet as a theory of quantum gravity on the world sheet, and 10 dimensions because that's where space-time comes out most naturally, okay, are the Majorana real, the places where you can both input spinors which are both chiral as well as real. Okay. On the other hand, let's look at dimensions 3 mod 4. Okay, those are so 6 dimensions, right? 5 plus 1 dimensions. SO6. So SO5 comma 1. So in 6 dimensions, okay, in 6 dimensions we have I should have written here real, and here we have pseudo-real. So in 6 dimensions, spinors are pseudo-real. Okay, 5 plus 1 dimensions, spinors are pseudo-real. You don't have real spinors, but you have pseudo-real complex chiral spinors. And in dimensions which n equals 2, which is 4 dimensions, the dimension of particular interest to us, okay, their spinors are complex. This is what Chintan said right at the beginning, that the chiral spinors and antichiral spinors under the Lorentzian notion of complex conjugation are interchanged with each other. Okay, also in dimensions in 8 dimensions, in 8-dimensional physics, 7 plus 1, 7 space and 1 time, spinors are complex. Okay, so what's to remember is that in 4 and 8 dimensions, spinors are complex. 4 we know. 8 also is complex dimensions. In 6, they're pseudo-real, but in 2 and therefore also in 10, they're real. These are the even dimensions. Okay, And what about the odd dimensions? The odd dimensions to remember is that we get real spinors in in 3 dimensions. That we knew, right? Sigma 1, sigma 3, and I sigma 2, real Pauli matrices. We get real spinors in 3 dimensions. And we also get real spinors in 9 dimensions. So 3 and 9 are real spinors. On the other hand, here we have 5 and 7 gives you our pseudo-real spinners. Okay, so in 5 dimensions and 7 dimensions you have pseudo-real spinners. In 3 and 9 you have real spinners. Good. Yes?
So 9,1 has
Real chiral spinners, yes.
once we go to Euclidean, which is SO10, they become complex.
Yes. So you see, as we said before, the same kind of, you could ask this question just about SO2. Okay? SO2 has complex spinors in Euclidean, whereas SO1, 1 has real spinors.
So it's like going from real axis to imaginary.
Yes, first, let's see algebraically how this happens. Okay? For SO2, the sigma matrices are sigma 1, sigma 3, and sigma 2. For SO1, 1, we can choose the sigma matrices to be sigma 1, sigma 3, and I times sigma 2. All sigma matrices are just completely real once we put that factor of I. It's impossible to find a set of all sigma matrices that are completely real in Euclidean dimension. Okay, so the algebra is there in front of your eyes. Okay? Now you can ask, how is this consistent? See, the notion of complex conjugation in Lorentzian space and the notion of complex conjugation in Euclidean space are different notions. Okay? So for instance, if you take the generator of time, okay, and demand that it be Hermitian, time translations, demand that it be Hermitian in Lorentzian space, it will become anti-Hermitian in Euclidean space because it picks up an additional factor of I. Okay? So once you do the analytic continuation, if you also analytically continue the reality conditions, what you will get is what you got in Lorentzian space. You start in Lorentzian space, do the analytic continuation to Euclidean space, but also analytically continue your notion of complex conjugation. Okay? Then you get the representations that you got of Lorentzian space. However, there is another notion of complex conjugation in Euclidean space. If you apply that, you get different reality properties. Okay? We will see this in many examples as we go on. It will become especially important in studying superconformal algebras. Okay? Perhaps, are you guys familiar with two-dimensional conformal field theory? Okay, so we see an example of that there. You see, in two-dimensional conformal field theory, so this is just an aside, just so that, yeah. In two-dimensional conformal field theory, we have this plane and we have the cylinder. And these two are conformally related to each other. As you know, suppose we were first in Euclidean space. Okay, so suppose we were in Euclidean space. Okay, then e to the power t tau, which is Euclidean time, is equal to r. Okay? Now, suppose that our real physics, as it is defined on the Lorentzian spinor, Lorentzian cylinder. Okay? So we've got this t coordinate that runs along the Lorentzian space. Okay? Now, if you have e to the power it and you complex conjugate it, this becomes e to the power minus it. After analytically continuing, e to the power it becomes e to the power tau. So if you complex conjugated it in Euclidean space, it would stay e to the power tau. But that's not what we do for physics. What we do for physics is to analytically continue the complex conjugation rules. So we demand that we work in Euclidean space with the rule that e to the power tau complex conjugate is equal to e to the power minus tau. Now, e to the power tau was the radius. E to the power minus tau is 1 by radius. So complex conjugation in Euclidean space on the two-dimensional plane comes with r goes to 1 by r. And this is the fact that Lm dagger is equal to L minus m. Okay? To say it again, if you just did the expansion in Euclidean space, this is such a weird reality condition to impose. Right? Because Lm and L minus m were the coefficients of 1 over z to the power m and z to the power m. You might have thought that the reality condition should be coefficient of z to the power m is related to z star to the power m. But the reality condition we impose, as you know, is Lm dagger is equal to L minus m, which is the coefficient of z to the power m and z to the power minus m are complex conjugates of each other. In Euclidean space, that's not what you get by complex conjugating. Right? But it is what you get if you follow through what you would have got in Lorentzian space by complex conjugate, as I've tried to explain to you. Okay? So this, I just wanted to say that this happens all the time in physics. That the reality conditions we impose in Euclidean space are not the Euclidean reality conditions. They are the reality conditions that come from Lorentzian space and then followed through after the analytic continuation. Okay? So there is a separate reality condition you might have wanted to impose in Euclidean space for some other reason. That will not be this one. Okay? So that is the reason why it's possible, in fact it happens, that Euclidean spinors with natural Euclidean reality conditions obey different properties from Lorentzian spinors. When you go to Euclidean space, you have to deal with those Euclidean spinors but with the notion of complex conjugation that comes from following through from Lorentzian space, which is not the natural Euclidean notion. It's this kind of notion. E to the power tau star is e to the power minus tau. Is this clear?
So it's not exactly complex conjugation.
It's not complex, it's not what a Euclidean person would have called complex conjugation. But it is what the Lorentzian person would have called complex conjugation. Okay? If you do that, then you will get all the properties of Lorentzian space. Is this clear? Yep.
So Hermitian conjugate also comes with 1 by z. Like pi dagger of z becomes Hermitian operator, that would be pi of 1 by z.
Exactly. R goes to 1 by r basically. You take star and also take r to 1 by r.
So 1 by z bar.
There's a minus sign there, but 1 by z. And right. Okay? So, you know, if you've studied conformal field theory, surely this has worried you at some time. Why is this the right reality condition to impose? It sounds totally weird, right? You take a function of z, complex conjugation should take it to a function of z bar. That's what Euclidean space would say. We don't do that. This is the logic. The notion of reality is inherited from Lorentzian space. We do this all the time in physics. Okay? We do this also for little group representation theory. I mean, for particle representation theory, for instance. You know, fields are representations of SOD minus 1 comma 1. When we analytically continue, they're representations of SOD. The natural representations of SOD are finite dimensional. We don't do that because finite dimensional representations would be Hermitian representations of SOD, but would be not unitary representations of SOD d comma 1. So when we analytically continue, we'll demand that we look at representations that in the natural SOD norm would not be unitary, so that they were unitary in SOD minus 1 comma 1. That's why we get infinite dimensional representations like fields propagating in space rather than some trivial finite dimensional stuff. Right? This is clear, right? Okay, so we do it all the time without thinking too much maybe. We must also do the same for spinors. Okay, great. Excellent. Okay, so all good. We declare, please.
Comment, I guess this analytically continuing the reality condition is what is responsible for what we say corresponds to unitarity in the Euclidean case, right?
Exactly.
Because the conjugate equals taking it out of
Exactly. Siddharth's comment. Siddharth's comment was that I tried to give you this business about analytically continuing in this radial quantization, in the cylinder map. But Siddharth's comment was, suppose we were not looking at a conformal field theory, for instance, just some ordinary field theory, or even in a conformal field theory, but we tried to do the analytic continuation more simply. Not in time on the cylinder, but time on the plane. Then that will tell us complex conjugation should be accompanied by reflection in t, because t must go to minus t. Same reasoning. But that is the condition of reflection positivity. So the statement that reflection positivity in Euclidean space maps to unitarity in Lorentzian space is another example of this. It's a great comment, thank you. Okay, any other questions or comments about this? It's very good you bring this up because, algebra is algebra, but the really interesting things about physics is understanding what are you doing, why are you doing this algebra, right? So these are really important points. So thank you for bringing this question up. Okay, any other questions or comments? Okay, great. So now that we're ready, we're going to say that we know everything there is to know about spinors. We declare ourselves to be masters of spinors. Okay, and we're going to use these spinors to develop the supersymmetry algebra. Okay, now these for that it is useful to set up an index convention. Okay, so now I'm going to move down here. Okay, it is useful to set up an index convention. I set one up in these notes. I hope I can find them. Yeah. Whenever I have a spinor, I will give it a lower index alpha. Okay. Gamma matrices act naturally on spinors. So they have indices like this. An upper index that will contract with the spinor index and a lower index that will give you back a spinor index. Okay. Now, what?
This is like commutator of gamma alpha gamma. What is this gamma?
Just any gamma alpha.
Oh, these are the single gamma.
The single gammas, but then also the product of two gammas.
Oh, yes.
Or product of three gammas. So any product of gammas will have this kind of index.
But their space-time index is lower.
Space-time index is lower, so I should have written that. This. And this gamma mu could have been gamma mu, gamma nu, so on. Okay. Now, let us look at this relationship with C. Now I hope I put the C inverse in the right place. Yeah, I have. Oh, let me look at the relationship with C, with transpose. Can somebody remind me what the relationship with C and C transpose is? Gamma alpha, how did it go? Gamma alpha was equal to, gamma alpha transpose was C inverse gamma alpha C star? You see C or the other way around? Up to but this way it's C inverse gamma C?
Yes.
Okay. Okay. And yeah. Right. C inverse gamma C. Pretty good. Alpha beta. Okay. So now look. What gamma transpose is doing is flipping first and second index of the gamma matrix. Okay, so it's flipping a lower index with an upper index and vice versa. So let's write this equation clearly. Okay, So this equation, let's write it out in indices. Gamma mu, okay, gamma mu, now I had alpha, let's say alpha beta, but because I've taken transpose, this has become like beta alpha. Okay, is equal to minus 1 to the power n, which plays no role. C inverse, let's call it theta phi, gamma mu, beta, thank you, beta phi, gamma mu, now gamma mu had the index structure that it had, which was lower with upper, so phi theta, and then C theta alpha. Okay, so for this equation to make sense, it's clear what index structure we want to assign to C. C is a matrix with two lower indices. Okay, because basically the role in life of C is to convert an upper index to a lower index. Okay, and so C inverse has two upper indices. Okay, so we write index structure C alpha beta. And the last thing to remember is that gamma 0, somebody will have to remind me, the thing that we used for reality, was it gamma 0 C or C gamma, I think C gamma 0, right? Psi star. What? Look at just the indices. There are no matrices here, there are just indices. I don't want to think in row and column. This alpha is an index. You can call it column or row, up to you.
Yeah, but why gamma has like one lower, one upper, while the C, which is a product of gamma, only has two lower?
See, it's true, can be built as a product of gammas, but its role in this representation theory is to lower indices, right? Its role, you know, it's a matrix. In our particular construction, it's some product of gammas. But its role, in every construction, what it will do is to transpose the gammas. Okay, so C as the object which achieves transposition has to have two lower indices, so that this equation becomes a covariant equation. Okay.
That is, I was asking that while constructing C, it seems like there are products of gammas.
Right.
One index will be lower, one index will be upper.
Right.
What matrix will you use to lower it further?
No, but that you know, what we are interested in asking is, you see, that would be the construction of a gamma matrix that transforms as a tensor under the Lorentz algebra. Okay, so there are two different things that in this construction happen to be the same thing. Okay, one is, in this construction it happens to be the case that C is proportional to gamma n plus 1 up to gamma 2n, or gamma 0, right? Okay, so this would be the same as gamma n plus 1, 0. This matrix transforms with upper and lower. Viewed as a product of gamma matrices, it transforms at upper and lower, and viewed as something which has upper and lower, it will transform under the Lorentz algebra like a tensor. Okay? So, you can think of it as a product of lower and upper, and then it will transform like a tensor. On the other hand, the role of this here is to be sort of a scalar, but not quite. It's like a scalar, but it lowers an index without also transforming in any tensorial way. Do you understand? Viewed this way, C is not associated with particular space-time indices. So the same object, if you allow it to transform under Lorentz invariance, like it would if it had two lower indices, plays the role of C. And like it would with one lower and one upper index, plays the role of a particular component of a tensor. Is this clear? Okay, right?
So you're saying that C is basically like a metric, which if you write C inverse, it's both of them are upper.
Yeah, when it's playing the role of C, when it's not a component of a tensor, C should have 2 lower indices, and C inverse has 2 upper indices, and it should transform under Lorentz transformations like it has 2 lower indices. Okay, okay, that's so the same object is given plays 2 different roles depending on its transformation properties. Okay, this is clear, right? Excellent. Yeah, that's again a very good point. And the last thing that we wanted was this object here. This object we knew had the same transformation properties as a spinor. So this object has a lower index. This is some alpha. But this object had a lower index have to be multiplied by a C. So this tells you that gamma 0 psi star has an upper index. So that when you multiply by C, you lower it. Okay? So this index structure is very important to keep in mind. Spinors have lower indices. Gamma matrices have 1 lower and 1 upper. C has 2 lower. And gamma 0 psi star has 1 upper.
Psi star then has an upper index.
Psi star is a funny object. To make it nice, you have to multiply by gamma 0. Again, you shouldn't think here of gamma 0 as being a component of a tensor, of a vector. Gamma 0 psi star is the object that has the upper index. Right? This was the point that, you see, gamma 0 psi star was the object that would transform, would transform in the dagger representation of SOD minus 1. Right? Because gamma 0 itself was not dagger, the dagger of gamma 0 was minus gamma 0. Okay, so mu, this gamma alpha beta dagger was not something nice. Okay, but when passing through gamma 0, it becomes something nice. So psi star doesn't transform in any particularly nice way, but gamma 0 psi star does. Okay, all clear? This, of course, is very familiar to all of us. This is what we call psi bar, right? And the way to write the Dirac-Lagrangian is in terms of psi bar, then gamma matrices and psi. When we write it like that, we can make it Lorentz invariant. Because psi bar has the inverse transformation compared to psi. Upper index means inverse transformation. So this is very familiar, just as an analog in every dimension. Is this clear? Okay, excellent. So now that we've got all our spinorialisms clear, we now are well placed to start writing down the supersymmetry algebra in every dimension. So we have maybe 7 minutes left. Let's do one dimension. Okay, so let's pick to start with an odd dimension so we don't have to deal with chirality. Let's suppose we do d is equal to 1 or 3 mod 8. Okay, so the space-time dimension is 1 or 3 mod 8. So we are doing SO2n plus SO2n comma 1 with n is equal to 0 or 1 mod 4. Okay, and the reason we're doing these dimensions D is total number of dimensions. The reason we're doing this dimension is you remember that when we had n is equal to 0 or 1 mod 4, which is same as d is equal to 1 or 3 mod 8, and we were doing SO2n comma 1, we had real spinors. Okay,
So now, as I motivated for you last time, our supersymmetries are going to be spinors. Our supersymmetry operators are going to be spinors in this dimension. We're going to choose them to be real spinors because we can. Okay, you want a complex spinor? That's fine. Just make 2 real spinors. Put an I, you get a complex spinor. So you lose nothing by choosing real spinors, but you can gain something because you can use one real spinor rather than even number. Okay, so our spinors are going to be real spinors, and let's say that we have many of them. So our spinors, let's say, take the form Qi alpha. Okay? So the question we're going to ask is, what is the anti-commutator of Qi alpha Qj beta? I is just which spinor, and alpha is the spinor index. Right, space-time spinor index. Okay. Now, of course, we want whatever we write down. Okay? We want whatever we write down. To start with, we've asserted that Q's are spinors. This immediately tells us what the commutation relations are between Lorentz transformations and the Q's. Because Lorentz transformations are what generate SOD, 1. Okay? So, M mu nu, with some choice of reality, we know already that M mu nu with Q alpha I, this is commutator, is equal to gamma mu nu Q alpha I. Gamma mu nu acting on the spinor indices. I can be more theta. Right, this is what it means for them to be spinors. So the commutator with M, we're going to just assert, is this. This is the statement that they are spinors. What about the commutator between momenta and the supersymmetry charges? Well, let's look at what we did last time in the quantum mechanics. They're Q squared to H, and the commutator of Q with H was just 0. We're going to take inspiration from that and just assert that all commutators between momenta and supersymmetries are 0. Roughly, the intuition is supersymmetry is like square root of momentum. Momenta commute with themselves, so we have supersymmetry commuting with momenta as well. Okay. So we will assert P mu Q alpha. This is equal to 0. What remains? We of course know the commutation relations between M and P and P and P. That's standard Lorentz algebra. M transforms like adjoint under itself, and P transforms like a vector under M and commutes with P. All that we know. What's non-trivial and what remains is just this part to complete the full algebra. This is clear? So to specify the algebra, I need to tell you what we can do here. Okay. Now, let's see. What could we write on the right-hand side that has indices matching? Okay, so one thing we could write, Schumann says, let's try to write a C alpha beta times something. This is one thing we could write. But this doesn't have immediately the feel of, it would be like Q with Q is a constant, right? In 0 dimensions, in quantum mechanics, we had Q with Q as H. What do you think should go on the right-hand side there? P. Now, what about P? What's the deal with P? P is a vector. We've got spinor indices. So what should we do? There you go. Okay. So we could try to do the following. We can try to write P mu gamma mu, which henceforth we'll write as P slash. Okay, so let me write it as P slash, just right now, so that it looks more elegant. We have P slash, but now P slash has indices alpha, beta. But that's easy. We can fix it by multiplying by C. So role in life of C is to lower indices. So now this has an index alpha, beta. Okay, we could write this, and we could write, now, last time, if you remember, the different supersymmetries here did very little to each other. So let's take inspiration from that and write a delta ij. And because Shuman has made a nice suggestion and we don't want to ignore all possibilities, we'll write zij times here. Just to see if we can get something interesting that we can generalize the algebra with.
And you are saying there are only two options.
There's nothing else you could write down. Right. Okay. So we're going to try to see now if something like this works. Does it work? Good. Gone. These are the supersymmetry charges. They are spinors. Why? Because we want something that squares to a vector. What did we get in quantum mechanics? We had Q with Q was H. The whole point of quantum field theory is to make that relationship covariant. H is just one component of a vector, which is P mu. So we want something to square to P mu. We want Q with Q to be P. So we want some representation that squares to, also they're anti-commuting, so it should be in some spinorial representation, some representation that by spin statistics has to be in spinor type representation. But something that will square to momentum. Spinor seems very natural. Okay? I'm giving you this rough logic, follow our nose logic. There are people who make theorems, okay? People who make theorems that say, there's this what Haag-Sonius somebody say theorem, which at least in 4 dimensions, probably generalized by now to every dimension, which says that if you want an algebra that has non-trivial commutations with the Lorentz algebra, non-trivial means it's not product of Lorentz algebra times something else, and allows for a non-trivial S matrix. It's not the kind of algebra that makes the theory completely free. Then these are the only algebras that exist. So people have looked at it seriously. Right now that would take us too far to try to, I could give you a reference to that theorem if you like. Okay, but right now we're just following our nose, right? We're just trying to see what worked in quantum mechanics and sort of generalize. Okay, it's a very natural thing to do, the spinorial thing, because square of spinor easily becomes vector. As we see, that's what a gamma matrix does. Okay, it's not the only thing we could have tried, I agree. But if you look at it seriously, nothing else works. You can try to make algebras, but all of them are so constrained that they don't allow for non-trivial scattering. They don't allow for an interesting theory. Okay, this first chapter of Wess and Bagger, the book by Supersymmetry on Wess and Bagger, gives you an outline of the proof of this theorem. Okay, in 4 dimensions, but okay, fine. Okay, so now I want to see whether it's really working. Always?
Symmetry?
Always. That's an excellent question. That's an excellent question. So it may or may not be symmetric. If it's not symmetric, then Zij would have to be antisymmetric.
Yeah, that is also okay.
Okay? If it is symmetric, Zij would be allowed to be symmetric. Okay? So this is the kind of thing we have to do. We have to check whether this whole thing is making sense. For instance, what are the symmetry properties of this? And really what we should do to convince ourselves everything is working nicely is to check all the Jacobi identities. You remember we started the whole class by talking about Jacobi identities that that superalgebras must obey. Okay? Really what we should do is to check those Jacobi identities. Okay, we'll do some of this kind of checking, but we keep that to the next class. We have to figure out various things. Okay, we'll do that more seriously in the next class. This will be sort of right with some symmetry property for Zij. One thing that Shuman's question already asks, is one thing we should be checking is whether this guy is symmetric. Right, because this by itself is symmetric and this is delta ij. Okay, that is something we should be checking. We will check whether this algebra makes sense. Yeah, it's similar to H with Q is 0. Okay, that's the intuition. Another way of saying it is that we know that P with P is 0, and Q with Q is going to give us P. So the easiest way for that to work is if P with Q is 0. There might have been other ways, but this is the easiest way for it to work. Okay, roughly, supersymmetry is like square root of translation. So since P commuted with translations, it's natural to expect it to commute with the square root of translations. Okay, we'll come back to developing this algebra in the next class, and hopefully by the end of the next class we will also start.